Down deep in the earth lies the treasure that makes our civilization run. Petroleum. Oil and gas supply 3/4 of the energy that fuels our society. But now these resources in the United States are fast running out, and we face a serious energy problem. At the risk of economic blackmail, we import 35% of our petroleum, and even that will be used up in our children's lifetime. We must develop new energy choices for the future. It will be a difficult task, perhaps the greatest challenge in our history. It is the challenge of the future. The Earth itself knows no energy crisis. The crisis is misdirected technology and resources. Today, we depend most on petroleum, our least abundant resource, but rely least on our most abundant resources. Now, we must begin a shift to other forms of energy. In the past, such changes in technology, as from wood to coal and from coal to oil, took 60 years. We do not have that much time. Many new sources must be examined. To coordinate this job, ERDA, the Energy Research and Development Administration, has been charged by Congress to meet the energy needs of present and future generations. Meeting the needs for the next generation may be the most difficult task. Alaska is one of the 5 richest oil regions in the world. The pipeline will eventually carry 2 million barrels of oil a day. But as demand increases and U.S. production declines, this great source will not be enough to maintain our present level of supply. Petroleum engineers are working hard to increase production on land and offshore. Most wells initially bring up only 15 to 20% of the oil. But secondary and tertiary treatment can force more oil to the surface. Now, as production moves to the outer continental shelf, oilmen develop new methods to drill in deep water while protecting the environment. If we can extend the life of our petroleum reserves, then we may have the time to develop new energy sources. More than any recent technological development, the automobile has changed the nature of our national landscape and affected our daily lives. It also takes about 1/3 of the petroleum used in the United States. Along with the automotive industry, ERDA is working on improved engines and components, alternative fuels and power plants, in an effort to increase efficiency and save petroleum. ERDA believes that a strong commitment to conservation by all elements of American society will be necessary to carry us through the critical years ahead. Great potential savings exist in industry, in residential and commercial buildings, and through conversion of urban wastes to power. Energy saved through conservation is better than any produced, for there is less environmental impact. From beneath our own lands comes another energy source, the greatest fossil fuel treasure we have. America has enough coal to last for hundreds of years and help give us needed energy security, if we can find ways to use it cleanly and efficiently. In its basic form, coal is bulky and expensive to transport. And with present clean air standards, much of it cannot be used without special equipment or processing. It contains polluting sulfur compounds. Coal is an important fuel for making electricity, but conventional generators get, at most, only about 40% efficiency. The remainder often contributes to heat pollution in streams and rivers. To solve these problems, ERDA, industry, and the universities are seeking new ways to burn coal. The fluidized bed method, for example, uses a mixture of coal and dolomite, a substance similar to limestone. In a boiler, this combination burns on a cushion of air, so heat is used more efficiently. The sulfur in the coal reacts with the dolomite and is retrieved before it goes out the stack to pollute the air. To get useful energy from waste heat, engineers are creating so-called combined cycles. By linking turbines and boilers together, the excess heat is recycled to raise overall efficiency. Researchers are also trying to develop a process with a jaw-breaking name, magnetohydrodynamics. Called MHD for short, it creates electricity without the friction of moving parts. Coal is pulverized and burned in a superheated flame. The hot gases, so intense they conduct electricity, are blown through a duct that is surrounded by an electromagnet. It has been compared to a rocket blast through a magnetic field. Through basic principles of physics, electrical current is generated. Like other fossil fuels, coal is primarily compounds of carbon and hydrogen. By reforming these mixtures under heat and pressure, liquid or gaseous fuels are created and pollutants removed. Scientists are hard at work to improve this technology. The goal is a national synthetic fuel industry whose products would replace dwindling supplies of natural petroleum. Liquids could replace crude oil for refineries or be used in the petrochemical industry. Already well developed are processes for making clean-burning, quality synthetic gas from high-sulfur coal. ERDA, in partnership with industry, is operating pilot plants. Pulverized coal is subjected to high heat and intense pressure and mixed with hydrogen. The product has the same energy content as natural gas and is low in pollutants. It is the kind of synthetic fuel that will be needed to replace diminishing reserves of natural gas. One of the greatest potential sources of synthetic oil, greater perhaps than Persian Gulf reserves, lies in the western United States. But freeing it for use without environmental damage will be a massive challenge. One of the several methods of extracting oil involves removing the shale by conventional mining techniques. But a large operation would dump vast amounts of waste on the land and use large quantities of scarce water. These problems may restrict the amount of oil recoverable through surface techniques. All synthetic fuel production involves some threats to the environment and uses large amounts of water, but underground processing may reduce these problems. So ERDA plans to test underground processing of oil shale on a pilot plant scale as another possible source of synthetic fuel to replace natural petroleum. During the last century, travelers in the American West navigated their way across the barren Idaho desert by using natural landmarks that stand above the horizon. Today, man-made landmarks point the way to progress in new forms of energy. Among them is the first nuclear reactor to generate electricity. Inside are the names of the men present at that historic event. During its first run, it generated only enough power to illuminate 4 light bulbs. "20 years later, nuclear power produces about 8% of America's electricity. Though more expensive to build than conventional units, in most cases, nuclear plants are cheaper to operate. 1 pound of nuclear fuel has the energy equivalent of 3,000 tons of coal. Enriched uranium is sealed in metal fuel rods, and these are bundled together in the reactor core. There, the action takes place in a controlled chain reaction. This causes heat, which creates steam, and that drives turbines to generate electricity. Like all energy systems, nuclear power has some drawbacks. Plants discharge about 50% more waste heat to the cooling water than coal-burning plants. The waste products must be solidified and stored permanently. Each application for a plant must be carefully reviewed for environmental impact and safety. Nuclear plants must compete with other energy projects for capital, materials, and labor. And there have been a few technical problems with the hardware of the complex systems. But nuclear power is a proven technology that can free our valuable oil and gas for other uses. One vast potential for unlimited power comes from the natural heat in the Earth's interior. The only commercially operated geothermal field in the United States is the geysers in California. Underground steam is tapped by conventional drilling techniques and piped to turbines to generate electricity. Eventually, this operation may create enough power to supply half the needs of the San Francisco area. But the geysers is in many ways the ideal situation. Clean, dry steam, easy to use to make power. Unusual circumstances for geothermal sources. Beneath the arid floor of the Imperial Valley lies hot, salty water. Technicians working for ERDA have used the water's own heat to desalt itself. Next, they plan to try and use this heat energy for electrical power. And in the Salton Sea area, one of ERDA's labs wants to put a high-pressure brine through a turbine to generate electricity. But they must develop special turbines that can withstand the corrosive effects of the salts. Many potential geothermal sites are found in the United States, each with its peculiar set of problems. The Raft River Valley is typical. Underground are geothermal reservoirs of hot water that can be tapped with wells. Some families near Burley, Idaho, have used this natural hot water for years to heat their homes and businesses. In new drilling, ERDA is exploring the potential of this hot water to create power. But because of its low temperature, about 300 degrees, low-pressure turbines will have to be perfected. In theory, there is potential for geothermal energy anywhere in the world, from the dry, hot rock deep in the earth. But power from this lies more in the future as geothermal technology continues to develop. The windmill may have been one of ancient man's first technical achievements, probably beginning in the area of Persia, but spreading through most of the world. Actually, at one time, windmills provided thousands of Midwest American farms with electricity. Now, radical new shapes of windmills of much greater size, using space-age materials, are being investigated for use in areas with constant wind. But before they contribute much energy, problems must be solved. How to store energy when the wind is not blowing? What lightweight materials can bear the stress of persistent motion? What kinds of axles and gears generate constant current despite the variable wind speeds? This new approach to an old energy source will help supplement our larger energy systems. No potential source is as clean and abundant as solar energy. A few homes in the United States have used the sun to help in central heating and hot water for some time, but problems remain that limit large-scale and widespread use of solar power. To help overcome these barriers, the government has begun solar energy programs. One project uses the sun to heat and cool school buildings. The schools, in different climatic areas, use solar energy to supplement their central heating and cooling, and to heat water for various uses in the physical plant. Though different manufacturers supply the hardware, most systems operate in a basic way. Water circulates through collector panels that trap the sun's heat. Pumped to the building's heating and cooling system, it exchanges its energy, or is stored for later use. Presently, solar collecting systems have high initial costs. Their contribution to total energy needs vary in different parts of the country. Nevertheless, ERDA sees a great future for solar energy. As part of the National Solar Heating and Cooling Demonstration, ERDA has been using a portable laboratory to calculate the sunlight received in various areas. This project will test solar heating and cooling units across the United States. The purpose will be to create the demand for a viable solar industry whose products would be dependable and available to the average homeowner. Further in the future is solar electric power. One system would concentrate the sun's rays to create steam for driving turbines. Its success will depend on finding ways of storing collected energy and converting it cheaply to electricity. Because of present high costs, commercial use of solar electric systems will come only after extensive development and demonstrations. But solution to these problems could provide an inexhaustible source of energy. One system directly converts sunlight to electricity with solar cells. Now they are handmade from individually grown crystals and are too expensive for a mass market. But scientists hope to develop new materials and mass production techniques to bring their purchase in the range of builders and consumers. It may be the next century before they have any significant impact, but prototypes of solar cells have already proven their worth in years of use on space satellites. And this very Earth, in partnership with the sun, offers another renewable energy resource. For growing here are all manner of plants that learned millions of years ago to transform sunlight into energy. Man, through biochemical processing, can convert agricultural crops, forest products, even urban wastes into energy forms such as methane and alcohol. Marine energy crops are also a strong possibility. One study underway with ERDA support would grow giant kelp for energy conversion. In the distant future, this fast-growing plant might be cultivated and harvested on large farms submerged in nutrient-rich ocean currents. The power of the ocean offers other potential sources of energy. The world's first tidal power plant is now in operation in the Rance River estuary in France. Reversible turbines in a dam across the estuary capture the power of the incoming and outgoing tidal surges. Few sites are available in the United States for similar operations, but in our offshore waters exists another potential for energy from the sea. Researchers are investigating how to build floating power stations that would use the temperature difference between the ocean surface and the deep water to create energy. In the long-term future, as petroleum supplies dry up, more of our energy will be delivered by electricity. As part of its work in conservation, ERDA is seeking ways of transporting electricity more efficiently. Because the ordinary electric cable loses massive amounts of power through resistance, scientists are now researching systems that would carry large electric loads with little loss of power. To take the strain off utilities now caused by wide peaks in demand, new ways to store electricity and ways to change it to other energy forms will have to be developed. Hydrogen gas, made from water by utilities during off-peak periods, could be transported by pipeline to supply many energy needs. Someday, giant flywheels, electromagnets, and large storage batteries may help carry us into a future world of energy. There will be increased demand for uranium enrichment as more nuclear power is needed to replace other fuels in the generation of electricity. By the turn of the century, perhaps half of our electricity will be generated by nuclear plants. Today's reactors get only about 1 to 2% of the energy potential from natural uranium. To raise this efficiency to as much as 60% and assure that our supply of uranium lasts for several centuries, ERDA is developing the liquid metal fast breeder reactor. The breeder consists of a central core of fissionable material surrounded by a blanket of uranium-238, which is in plentiful supply. During operation, the uranium-238 is transformed into fissionable plutonium, which can be used to fuel other nuclear reactors. Today, ERDA scientists and scientists in several countries are developing the systems and the components that will go into the breeder. And in partnership with a group of electrical utilities, ERDA is building the first large-scale fast breeder demonstration plant. If developments are successful, and if social, environmental, and safety standards can be met, then the liquid metal fast breeder could help assure supplies of electricity into the next century and beyond. In the seas lie the clues to the origin of man. Therein may also lie his hope for the future. Limitless supplies of energy fuel from ordinary water. Through the wonder of fusion. The mechanism that powers the enormous energy of the sun. The stars that gave birth to the universe itself. Now, man is trying to duplicate this process for an endless source of power. Fusion happens when atoms of hydrogen are brought together with such force that they fuse and create energy. The fuel for this process would be deuterium, cheaply obtainable from water. It would take place in the form of a plasma, a gaseous material which comprises most of the universe and such everyday things as the inside of fluorescent lamps. Since it reacts to magnetism, the major effort has been what is called magnetic containment fusion. Its greatest problem has been keeping the plasma stable long enough to cause a fusion reaction. Today, scientists in several countries are cooperating in work on a variety of fusion devices. ERDA's program includes several different magnetic containment machines to examine fusion problems. The first American test reactor is scheduled to begin operation in 1981. But even if things go well, it may be after the turn of the century when commercial fusion operations begin. The challenges to the creation of fusion power are great, but the rewards are monumental. It could mean a limitless supply of fuel available to all people, a system that would use water to run our civilization for millions of years. A newer line of fusion work is with lasers, the incredible machines that create pure, orderly, and intense beams of light. Since lasers themselves were only invented in 1960, much more has to be learned about them before they can be proven to work for commercial fusion power. A laser fusion machine would be gigantic, generating several powerful parallel beams. At the end of the mechanism, they would converge on tiny pellets of deuterium and tritium, causing the pellets, a succession of several each second, to implode upon themselves and produce fusion reactions. We are now entering a new era, a time when energy, at least for the rest of this century, will be more expensive and less abundant. All new sources will mean some cost both to environment and economy. The future will be a challenge to us all. We must conserve and be efficient with all forms of energy. We must depend more on our own energy resources and less on petroleum. Now, while we still have the time, we must develop new energy technologies for the future. This challenge of the future will be met not only in our research labs, but in our industrial plants and our homes. How well we meet that challenge will determine the shape of civilization to come.